Today we want to start looking at our other big question in calculus. We divide calculus up into two major sections. Overall, we're thinking about the study of infinity and the difference between the discrete and the continuous, and how we use the discrete to model the continuous. This requires that we have a pretty good understanding of what a limit is and what we mean by infinity, how we can rigorously talk about infinity. So we really want to use the discrete to model the continuous. One of the problems that we had there is, what is the slope of the line tangent to a curve at a given point? Problem there is that slope is change in y divided by change in x, but if there's only one point, then change in y and change in x are both zero. So really that question comes down to, what is 0 divided by 0 in a given case? So the same thing happens when we get to finding the area under a curve and above an interval. We want to find the area under a curve and above an interval. We want to use the basic idea of area. Area is just a length times a width. That's just how much space a flat thing is taking up. So I want to use area is equal to length times width, but the length is continuously variable. So I've got different values for the length at each different real number, and that is a problem. The variable part is easier part to deal with. We multiply when things are constant. We get to multiply when we're trying to add things up and they're constant. But if things are variable, we're going to use addition. So just dealing with the variable part, not too big of a deal. We're just going to use addition. Addition is what we do when we don't have multiplication, when things are not the same. But this continuous is a problem because there's nowhere to put the plus signs. So we're going to use a discrete area to model the continuous area. So we want to use addition, but this continuously part says, but there's nowhere to put the plus signs. We want to use multiplication, but one of our factors is variable, so we're going to use addition. But that factor is continuously variable, so there's nowhere to put the plus signs. So we're going to use a discrete sum to model the continuous sum. That's just the next step. Use a discrete sum to model the continuous sum. I want to write a sum, but a sum means I'm putting pluses all over the place. In a continuum, there's nowhere to put the plus, so we're going to have to use a discrete sum to model the continuous sum. So if I want to find the area, say, under this curve and above the interval from 0 to 3, we just break it into some smaller rectangles. And I say, if we look close enough, the thinking is that if we look close enough, since the function is continuous, if we look at the function close enough, if we look over a small enough change in x, then the value of the function won't change that much. So this is the baseline thinking that we're going to apply. If we look over a small enough change in x, then the value of the function won't change that much. If we consider a small change in x, then the change in f of x will not be large. Then we'll have a small change in f of x. This small change in f of x, we're going to say, is no change. We're going to model this small change in f of x with constant, with no change. We're going to model this small change in f of x as no change in f of x. We make delta x very small, then the change in f of x will be very small. And we're just going to say, let's ignore that change and just keep it constant. Keep f of x constant. If we keep f of x constant on all these delta x's, on all these small changes in f of x, or sorry, all these small changes in x, then we get to take care of both of these problems. We have a place to put the plus signs because we have small changes in x, and we get to use multiplication because I have a constant height or a constant length. This takes care of both of our problems. This will give us a place to put the plus signs. So what we're thinking is f of x is constant for delta x. So for some small delta x, we get to say f of x is constant. This gives us two things that we want. Takes care of both of our problems. First, it allows us to use multiplication because I have a constant length multiplied by some width, and we also get a place to put the plus signs because I'm using all these different delta x's. I have a countable set of delta x's. Gives us a place to put the plus signs. And we get to use multiplication. Where the length is just the value of the function, evaluated at some point, and the width is just the width of our interval. The distance, the change in x over which we're saying the function is constant. Yes, this is how this is the thinking behind a Riemann sum. We're just modeling the thinking behind a Riemann sum. So in our example here, I've only got 3 subintervals, 3 delta x's. But what we would do is pick a point in each of these subintervals and say that the height of the function, so here's x1, I've only got 3, so x1, here's x2, and here's x3. I just need to evaluate the function somewhere on that interval to get a height. So at each of these points, I'm going to say whatever the value of the function is at x1, that's the value of this function for that entire delta x. Then whatever the value of the function is at this x2, that's the value of the function for this entire change in x. And then whatever the value of the function is at x3, same thing. So here we've got three intervals with the width of delta x. And here's how we build the Riemann sum. The area of each of those intervals, the area of this first rectangle is just f at x1, that's the height, times delta x. That's our first rectangle. Our next rectangle is f at x2 times delta x. And our third one is at f of x3 times delta x. We get to use multiplication because our length is variable. We're assuming our length to be variable in this model. We model that variable length with a constant length, because if we do this enough, the function is not changing that much. We also get to a place to put the plus signs. We just add up these three areas. And we get the approximate area. Then we improve our approximation with more rectangles. That's when we start writing things with a Riemann sum. Here we have n rectangles. We'll evaluate the function at some point in each interval, and then multiply by delta x. Then we do the Riemann sum thing. We do the calculus thing. The calculus thing says more rectangles means a better approximation. Just do infinite rectangles. Whatever you do to improve your approximation, do that forever. That's the calculus way. Whatever you're doing to improve your approximation, you created a model, a discrete model of a continuous thing. Whatever you do to improve your approximation, do that forever. Use an infinite number of rectangles. Make the 2 points that form your secant line infinitely close together to get your tangent line. Same kind of thinking. Now, the important thing is what this translates to. So we know that this translates, so the big thing in calculus is that this Riemann sum will pop out a definite integral. The Riemann sum, when we take the limit as n goes to infinity, the Riemann sum becomes the definite integral. This is the big reveal. Look how much the form changes. Look how much the form doesn't change. Rather than have this discrete f evaluated at this one point a bunch of times, or at these n points multiplied by delta x a bunch of times, our delta x is becoming infinitely small. This dx is our infinitely small delta x. Not zero, just infinitely small. And we're not evaluating the function at a bunch of discrete, at a discrete set of points. We're adding up this f of x times delta x at all these points, at all those points from A to B. We're now plugging in a continuum. The integral is telling us what values of x to do this calculation at, and it's saying it doing all the points from A to B. Then the next stage, this is where we've gone from the discrete. We do this forever. We end up with a continuous sum. This is our continuous sum. The definite integral is our continuous sum. The Riemann sum, which is a discrete sum, becomes our definite integral, our continuous sum. And then, of course, this is our favorite because we know that we can evaluate a definite integral with an antiderivative. Our fundamental theorem of calculus says we can evaluate the definite integral with an antiderivative. Then, of course, the other part of the fundamental theorem of calculus says you can construct an antiderivative using the definite integral. And then later on this semester, we learned that there's more fundamental theorems of calculus. They're like Skywalker. We just make more of them. Only, at least in the case of calculus, more fundamental theorems of calculus make sense. Any questions? Now, this is all old stuff. Everybody here is like, oh, dude, we knew this because we've been through Calc 1. And then you said this shit again in Calc 2. Why are you saying it again now? Because the thinking is important. We're going to be doing the same thinking when we upgrade from a function of one variable to a function of two variables. So the question was, we're using a series of discrete values of tiny changes to approximate the infinite continuous value represented by the integral. Yes. So we're modeling the continuous change with discrete changes. We're modeling the continuous with the discrete. We have a discrete sum with a countable infinity of rectangles. And then that becomes this continuous sum, which is what we're trying to do. Revealing that these two things are going to be the same, that's a big deal. And then even further, this is useful because we can find an antiderivative of this function. So we can calculate this area with a definite integral. Sorry, we can calculate the definite integral with an antiderivative. Here's one of the things that, here's the way we want to be thinking about this symbol right here, because this is a symbol that's going to have to get upgraded. And this is why we went through all this. We're calculating f of x times dx at all these values of x. We're taking f of x times dx at all the values from A to B and adding them up. It doesn't make sense when we say it like that because all the values from A to B form a continuum. And so we can't evaluate the function at all the values from A to B and then add them up. There's nowhere to put the plus signs. That's still a problem. We have ways around it, but we still want to be thinking of that. This symbol says evaluate f of x times dx at all these values from a to b, at all those x values. The integral symbol is telling you what to plug into the expression f of x dx. That's what what we want to see when we look at this expression. So when I see the expression integral from a to b of f of x dx, I'm reading this as evaluate f of x dx at all the values from a to b, and then add them up. So we're going to think about evaluating. For those of you not color coordinating. First, we're thinking evaluate the expression f of x dx. The integral from a to b says at all these values of x, and then we add up the results. This is very suspicious because where do we put the plus signs? And the answer is, don't worry about it. We have ways of getting around that, specifically the antiderivative if we need to. Or phenomenal computing power in an itty-bitty space. This is just the thinking that we want when we see this integration symbol. All just how we're thinking about that symbol. Because we want to be able to read what different versions of this symbol are going to be telling us. So that will make sure that we know what's required when we start filling out these symbols, when we write these things down. Time to upgrade. A function of two variables is our next upgrade, just like at the beginning of class, a function of two variables. We're thinking of this as a surface, a two-dimensional surface in three-dimensional space. So we need to upgrade, we've upgraded our functions to functions of two variables, no longer representing one-dimensional curves in two-dimensional space. Now our function of two variables represents a two-dimensional surface in three-dimensional space. So now, instead of the question, what is the area under the curve and above an interval, instead of what is the area we don't have area, curve, and interval anymore. Those are the three things that are going to have to get adjusted. Instead of asking the question, what is the area under a curve and above an interval? Now we're not under a curve anymore. We're under a surface. So we've upgraded our curve to a surface. Now, underneath the surface is not going to be an interval anymore. Before, life was easy because we were just on a number line. All we had was x's that are being plugged into the function. But now I've got a bunch of points that are x's and y's. So an interval is just made up of a bunch of x values. All we can say is start here at A and end here at B. That's the only subset of the number line that we have. It's our one-dimensional subset. But now I have a bunch of x's and y's. Now I'm plugging in a bunch of x's and y's. So instead of an interval on the x-axis, I'm going to have some x's and some y's. We're going to describe that as a region. There's going to be this area, this region on the floor. Think of it as the floor. Our surface is a function of two variables. Since we have a function of two variables, I have a bunch of x and y that I'm trying to plug in. And if I've got a surface above and this area below, the space in between is not going to be an area. The space in between is going to be a volume. Before, we were calculating the area as the space between curves, but now we're calculating the volume as the space between areas. Area was the space between curves, the function, and an interval. Volume is the space between surfaces or regions or areas. One area is the surface above, the other area is the region below. We're upgrading our old question. Same question, same thinking. But instead of what is the area under a curve and above an interval, what is the space between these curves? What is the volume under the surface and above the region? What is the space between areas? The rest of it is going to be the same calculus thinking that we've always had before. Our surface is going to be continuously variable, but not just in one direction now. Our surface, which is going to be the height above the region, is going to be continuously variable, changing with x's and changing with y's. We're going to apply the same thinking. If our surface is continuous, then a small change in x won't have a big big effect on the value of the function. And if y doesn't change very much, then the function won't change very much. So we're going to think of the surface, this continuously variable surface, as being flat for a small change in x and for a small change in y. That will allow us the same things that it allowed us before. It allows us to use multiplication, height of the function above the delta x times delta y for the volume, and it gives us a place to put the plus sign. I add up all these little rectangular solids. Then we do the same thing. Let the number of rectangular solids go to infinity. Write a definite integral and presumably evaluate it with an antiderivative. Like I said, Calc 3 is the easy one because we're doing the same thinking. Let's look at the simplest example. The basic thing that we're trying to do, volume under a surface and above an interval. I'm going to make things as easy as possible. I'm going to make the surface flat. I'm going to make the surface constant. And I'm going to make the region a rectangle. I'm going to make everything fit into the simplest possible. So I've got a y-axis. Let's go this way with the y-axis. Go this way with the z-axis. Let's give ourselves a simple region to work with. Let's say from 0 to 1, 2, 3, 4 on the y, and 2 on the x. This is why rectangles are so great, because it's just the intersection of two, or it's just the combination of two intervals. Then the simplest thing to do would make the height constant. We can make our surface a nice flat surface. And we will want to calculate the volume of the space between these two areas, or these two areas. So the volume is the space between the area. This is pretty straightforward. We just calculate the area of the floor and project it through the height, which is constant. In this case, we get to use volume is equal to area times height. In this case, we get to use volume is equal to the cross-sectional area multiplied by the height. We get to use multiplication because our height is constant over the entire area. We get to use multiplication because the height is constant over the area. This is the kind of thinking that we want to think. We want to think about the area, that little piece on the floor, and multiply it by the height. Because this is the shape that we're going to use. This is the thinking that we're going to use when our surface stops being flat and starts being continuously variable. I'm going to just think of the region as a bunch of little rectangles. I'm going to think of the region as a bunch of little rectangles and calculate the height at one point on all those little rectangles. Any questions? I guess the volume here would just be 2 times 4 is 8. That's the area of the floor. And it's the same all the way up. So times the height 5. So 40. Any questions? Calculus thinking about the next thing. Once we have this thinking down, we're going to want to translate this into an integral. We're going to want to take our discrete sum and write it as a continuous sum, that is a definite integral. All right, that's going to do it for today. Think about this expression, this definite integral, evaluating the expression and all those values of x. Think about how that's going to have to change when we start dealing with volume under a surface and above a region. That's it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.